It's a real pleasure to finally have Ivan Corwin come and give the colloquium. This has been much delayed, and we had hoped that to have him in person. Hopefully, we will do that again some other time in the future. But for today, he will zoom over and tell us about stationary measure for the open KPZ equation.
Okay, well, thanks, Shmuel. And yeah, I'd love to come in person. We've developed a little bit of a pipeline between Columbia and Chicago now. So, a number of students and postdocs are at Chicago. So it's a lot of fun. And actually, this work is with a former postdoc of mine who's now a professor in statistics at Chicago, Elisa Kniesel. So, this is going to be a talk about the nature of stationary measures for Markov processes. And that's a general question, and there's a lot of interest in it. So the identification and classification of these stationary measures for Markov processes is really fundamental. And it relates not just to the long time behavior of processes, but to all sorts of other phenomena associated to them. If you're very lucky and you deal with pretty simple systems, you find measures which take product form. So kind of a very simple example is if you have a cycle and you have random walks on the cycle, so multiple random walkers. If you start off with a Poisson number of random walkers at every point in the cycle, so some random number of walkers and randomly located, that property will be preserved for all time. So this sort of product Poisson structure is preserved by the evolution of these random walkers. Another class of measures that one often encounters are what are called Gibbs measures. So if you've ever seen like tiling models, you look at like the uniform random tiling, or if you've looked at the Ising model and looked at the Ising measure, these are Gibbs measures. They involve kind of energies that are local functions of a configuration, and then you exponentiate that. and these often will also form the invariant measures for certain types of Markov processes. We'll be talking about a more complicated class. So we'll focus on the KPZ equation and a model related to it called the asymmetric simple exclusion process, which has boundary conditions. And the presence of boundary conditions will break the simplicity of these invariant measures. So if you didn't have boundary conditions, you'd have very simple invariant measures I'll describe. But it breaks the simplicity of it, and it creates a very complicated structure for the invariant measure. Yet we'll still be able to analyze it. So the sort of physical goal of this talk, there'll be a physical goal and a mathematical goal. So the physical goal of this talk will be to really understand the nature of boundary conditions and how they affect stationary measures for Markov processes. You can kind of think of this as a model for the type of processes we're looking at. Imagine you have a lake and you have a river, and it's connected with a stream. And the stream transports water from the lake to the river. Now, obviously, there's movement through the system, so it's a sort of non-stationary system. But if you just look at the profile of the stream, that will be statistically stationary. It will tend to look in certain ways. It may be rise and fall based on the seasons, but statistically, it will be something relatively constant over time. And so we'll be looking at systems of this sort. Mathematically, my goal is to explain to you the role of integrable probability and stochastic analysis and how these two tools can come together to shed light on questions which really can't be answered on their own. So that this is maybe setting the stage for what we're going to do. So let me share the screen now. And okay. Okay, let's do side by side. Okay, so the talk is on the open KPZ equation stationary measure with Lisa Kniesel. And what I'm going to start with is something completely different. So I just gave you a preview of what the talk is about, and now let me tell you something different. So the first 5 minutes of the talk is going to be about Q-Ponchhammer symbols. Okay. Now, I'm not just doing this because they're beautiful, though they are. I'm doing this because they end up being a very important tool in the sort of nitty-gritty of what we're doing. And I won't go into details about that, but I want to just give you the flavor of one nice piece of mathematics that comes in. So you may have seen these before. They're written as AQ, then usually a natural number, but I'll take infinity. And it's an infinite product, 1 minus a, 1 minus a times q, and so on and so forth, a times q squared. And provided that q is of modulus less than 1, this will be an absolute convergent product, and it will define an analytic function in the parameter a. Okay. Now, why might one be interested in studying these, or where do they come up? I'll give you a few examples. So in combinatorics, they often relate to nice generating functions. So if you take minus q infinity, which is, in other words, 1 plus q times 1 plus q squared, 1 plus q cubed product, you can expand this combinatorially as a sum over what are called strict Young diagrams of q to the size of the Young diagram. Okay, so a Young diagram is usually denoted by a collection of boxes, and it corresponds to a partition. So here the partition would be 4, 2, 1. So it's a weakly decreasing sequence of natural numbers, and strict just means it's strictly decreasing sequence. So you sum over all possible Young diagrams, q to the size, so the size would be 7 in this example, and this has a very nice product form. This is not a hard fact, but it's still nice. If instead I wanted to study the sum over all partitions of q to the size, that also has a nice expression as 1 over q infinity. And this one is marginally, slightly more complicated. It just requires using the geometric summation formula, and then a little bit of thinking. So both of these indicate already that there are interesting combinatorics related to these q symbols. There's also interesting probability related to them. For instance, if we assume, and obviously here I'm assuming this q is less than 1 for this to be convergent, these sums. If I assume actually that q is between 0 and 1, then every term here on each of these terms will be a positive number. And so I can divide through by the left-hand side, and this actually defines a measure, right? Because I have a sum of positive numbers that sum to 1. And it defines, in the first case, measure on strict Young diagrams, and the second measures on just Young diagrams. And these are measures that are generally concentrated on small diagrams, but as q tends to 1, the closer q gets to 1, the more that they'll favor larger and larger diagrams, in the sense that there are more there are more diagrams that are large than small, and so there'll be an energy entropy interplay. And as q goes to 1, you can ask stuff about, well, what are the limits of these measures on strict partitions or on regular partitions? What are the fluctuations? What are limit shapes? And all of these are questions that can be answered and have been answered in various forms. So this is one motivation to study these q symbols, and in particular, q goes to 1 asymptotics. Now, one other motivation is that there exists very nice q deformations of classical special functions, and things like orthogonal polynomials and just things like the gamma function. So this is what's called the q gamma function. So you take 1 minus q to the 1 minus z, q infinity over q to the zq infinity. Now that doesn't look like a gamma function, but if you take q goes to 1, then this actually converges to the classical Euler gamma function. And this is not a terribly hard thing to prove, but it's not entirely trivial either. So already you see that these sort of q deformations are quite interesting. So here you get a nice product form. Now, on the subject of taking q to 1, we know that for the usual gamma function, there are all sorts of interesting asymptotics in the complex plane. For instance, Stirling's formula for z with large real part, and also decay estimates for a large imaginary part. And so you might want to know something analogous for the q gamma function. And so this is a subject that's been studied for the last 30 or so years, and there are various results. And I'll tell you one result, and this is a refinement of things that were known. I'll tell you what's new. So you take q going to 1 like e to the minus epsilon going to 0. And now we look at this, the important part of the q gamma function, right? Everything about this is pretty pretty reasonable except for the denominator. This is the most complicated part. If you understand that behavior, you understand the full behavior of the Q gamma function. I'm going to look at the logarithm of that because as Q goes to 1, I'm going to be looking at a lot of terms like 1 minus 1, right? Or 1 minus something close to 1. So that's a product of a bunch of things close to 0. So their product will be really, really close to 0. So I should really quantify that by looking at the behavior or the decay of the logarithm. So first of all, you can kind of do a heuristic that tells you that it should decay like a negative constant times epsilon to the minus 1. That's the sort of first guess that you would have. The question is, what's the constant? And it turns out that it's zeta of 2. Already, this is kind of a cool thing, I should say. Then there's a correction, which is really, well, if you take the logarithm, it's log epsilon order, or if you didn't, it's polynomial order. And then finally, there's the gamma function is showing up in the order 1 asymptotics. And then there are lower order terms, terms that go to 0 as epsilon goes to 0. And you have actually similar sort of asymptotics for the Q, the minus sign, except now you have lots of terms which are like 1 plus something close to 1. So that will actually have the opposite sign. That'll have growth. And it turns out that it has that it has 1/2 of the growth rate, but in the other direction. And then there's similar sort of asymptotic term, but actually it's not log epsilon, it's log 2. And then there's lower order terms. Okay, so I should say everything that I wrote down is what was understood. The question which ended up actually being very important for us is to understand the nature of these lower order terms. So you can find results where people have kind of said if you fix epsilon and take z to be large in different directions, these are the asymptotics. Or if you fix z and you take epsilon. It turns out that we need very strong uniform results in both epsilon and z, where z can vary in the entire complex plane and epsilon is tending to 0. And this is something that turns out to be very important in our story, as well as, if you imagine, it could be very important in other sorts of asymptotics. So I won't go into the detail of these uniform. I'm just mentioning this as a sort of key technical detail. Now, why did I start with this? Well, if you get bored during the talk, try to prove any of these things. Okay, maybe start with the first ones, but there are 5 things that you can try to prove. Hopefully you've written them down, and you can always come back to that if I lose you later in the talk. Okay, so with this in mind, let me move back to the main subject, which is the open KPZ equation, and in particular, its stationary measure. So I'm going to consider a time parameter t bigger than or equal to 0, space parameter x in 0, 1, and I'm going to look at something I'll call a height function, which will be indexed by time and space, and it will take values in R. Now this h is going to be the solution to a stochastic partial differential equation, which I'll talk about. I'll write it down first. So this is that the time derivative is, this is an equation is called the KPZ equation. This will be a special case of it. If you've ever seen talks about this, you will have seen a little bit about this equation. So it's a Hamilton-Jacobi equation with the quadratic term, and then some squiggle. And this squiggle is an object called space-time white noise. It's what makes this random. In the same way that if you've seen a stochastic differential equation, you'll have the presence of a one-dimensional white noise driving it, or basically a Brownian motion driving stochastic differential equation. This is a spatial version of that. Now, because we're dealing in a finite interval, we also need to impose boundary conditions. And the boundary conditions will be imposed at 0, and they'll be imposed at 1. And so I'll just take what are called Neumann boundary conditions. And there's a reason I put a minus sign, but let's not worry. So this is for every value of u and v. So we take u and v to be in R. This should define an equation, an evolution. And it'll be somehow a function of the white noise, and it will give you a spatially evolving system. So let me kind of draw a picture for what you should have in mind here. So, we have the boundary of our system. So here's 0, here's 1. And let's say I start out at time 0 with some sort of profile that looks like this. Okay. Now this is my height function. This I would call h0 comma dot. This is the height function, function of dot at time 0. Now it evolves, and so maybe at some later time it looks like this. And a later time it will look, you know, a little bit more like that. And it continues. Now, obviously, it could actually go the other direction. It doesn't need to go monotonically upwards. I'm drawing it that way for simplicity. The boundary conditions are somehow imposing that the slopes at this boundary should be u, and the slopes at this boundary should be minus v. The reason for the minus sign is sort of a physical thing. There's a symmetry between the two sides, right? So really, from the perspective of the right boundary, the slope is v, and from the perspective of the left boundary, the slope is u. So that's why it's kind of natural to put a minus sign on the right boundary. Now, I'm going to ask 3 questions about this evolution. So the first question is, what the hell does it actually mean? What does it mean to solve the KPZ equation? And the issue here is that this is actually not a well-posed equation. What do I mean by that is, so, you know, the meaning of each of these terms, so this is some sort of smoothing term. Right? This is, you have a growth and it's smoothing itself over time. This is some sort of mechanism for lateral growth, saying that you kind of tend to grow in the outward direction, or, you know, with a slope dependent rate. And this is the noise that's driving the system. Now, the issue is that if I were to try to make sense of this equation and got rid of the lateral growth term, so to somehow simplify the picture, then I will have an equation that you can check has spatial solutions that are Holder 1/2, well, 1/2 minus, so just slightly less than Holder 1/2. And if I then try to put the nonlinearity back in, I can't make sense of it because I can't really define the square of the derivative. Now, there are ways to make sense of it. And one way of doing that is through smoothing the noise and trying to then make sense of the smoothed equation and removing the smoothing. And this can be done. But it turns out that doing that is the same as doing what's called the Hopf-Kohl solution. So the first thing that I'll explain to you is what is the Hopf-Kohl solution? So what does it really mean to solve this KPZ equation? Okay. The second thing, let me use a better marker for this. Okay, so what does it mean? The second thing the second question is, how does this equation arise? So does it arise as scaling limits of some simple physical models? And the third is, what does it look like? And what I really mean by this question is, if you look at the equation after a long time, what will the profile, the height function, look like? So let me first address the question of what does this equation actually mean? How do you properly define this? Because we should actually work with a well-defined object. And the definition is as follows. So I say that the solution, HTX, is actually defined to be the logarithm of something I'll call Z, where Z solves the stochastic heat equation. So this, where Z solves the stochastic heat equation. So the stochastic heat equation is another stochastic PDE. The reason this is called the Hopf-Kohl solution is if you've worked with things like the Hamilton-Jacobi or the Viscous-Burgers equations before, you know that for quadratic flux, there's a transformation, just an exponential transformation that transforms you into a multiplicative heat equation, where the multiplicative term has to do with the forcing of the stochastic of the Burgers or Hamilton-Jacobi equations. And so this is the same transformation, but being applied with stochastic forcing, with random forcing. So this is what the transform equation, the sort of exponentiated equation, looks like. And the boundary conditions become Robin boundary conditions. So if you look at 0, or you look at 1, you have some Robin term. And for reasons that I'm not going to go into, it's natural to actually have some sort of correction by a half. So this is just a matter of convention because I'm actually defining what this equation means. But for some physical reasons, you put in a factor of a half. Okay, so this is the equation that one is really interested in. If you can solve this equation, you take its logarithm, and this is what one means by solving the KPZ equation. Now, obviously, you need to match up the initial data. Now, solving this stochastic PDE is actually something that can be done in a classical way. You don't need to do any smoothing or anything complicated like that. Though you do still need to make sense of it because it's a rough equation. And so even taking these sort of spatial derivatives, this is not a well-defined object. You know, you can't take the derivative of something that is Holder 1/2 because it still will have that same Holder regularity. So what you actually end up doing is you rewrite the equation in an integrated form and you solve that equation. And so what you really mean, so this is really equivalent to finding a solution to the following equation, which is you take the heat kernel. So this is the Robin heat kernel. So you take the heat kernel that satisfies exactly these same boundary conditions and this equation, but without the noise. So if there was no noise, the solution would just be this convolution of the heat kernel with the initial data. Okay, so that's the solution when this term is gone. But in the presence of this term, you also need to constantly be re-inputting the noise from the forcing from each different time. And so you have the classical Duhamel form of this equation. So you take the heat kernel at a time t minus s and you convolve it with the time s spatial process given by the forcing term. And then you evaluate that dx, and then you integrate in s. Okay, so this is actually what you mean by solving the stochastic heat equation. And at this point, you can actually just use Picard iteration to show that there exists a solution to this equation. Okay. So you do this Picard iteration scheme, and this will actually define an infinite series, which is called a chaos series. And this will be a solution, a strong solution for the stochastic heat equation. Okay, so if I lost you, I'm done with the stochastic analysis. I just wanted to explain to you what this equation really means. We'll see another meaning for it in terms of scaling limit in a little while, but one should know what you're working with. So the real question I'm interested in is not how do you make sense of the equation, let's assume it's made sense of, but rather the question is, how does the equation behave if I run it for a long time? I'm looking at some sort of random interface growth. So the first question that I ask is there a long time limit for h, ht dot? So I'm looking at the spatial process at a time t, and so I keep running it, and I run it and run it, and what you kind of can see is that the answer is no. There's nothing about the equation which tries to hold you to a particular level. There's no force that pushes you back towards zero. So even if you don't drift away, the way I've drawn it, it looks like it's drifting positive. Even if you don't drift away, you'll just diffuse. So the height function will spread out. And so there will be no limit for the height function. In the same way that there's no limit for a random walk on z. A random walk on z diffuses. So there's no stationary measure for that, stationary probability measure. But there will be for the increment process. So the answer will be yes if we look at ht dot minus ht0. So if instead of looking at just kind of in an absolute frame, if I look at everything kind of as compared to the value at 0, and then I look at the spatial, the increment process, that will have a limit. So for instance, if I look at the distribution of the height increment, right, the difference between the height at 0 and height at 1, that will have a statistical limit. That'll converge to something in distribution. And actually the entire profile should converge to something in distribution as well. And so that's in a sense, that's the real object of interest, which is what is that limit going to look like? So And that's what you would call the stationary measure. So let me define, just to be careful, I'll say that at an initial data, so an initial height function is stationary if the law, so the distribution of the process at time t started from that initial data and centered by its value at 0 is t independent. Okay. So this is the same as if if you're doing card shuffling, right? If you shuffle your cards, you start out with a shuffled deck, totally random deck. You keep shuffling it, it'll stay shuffled. Obviously, if you start out with a non-shuffled deck, it'll eventually become shuffled. So the theorem that Elisa and I prove is an identification of stationary measures for this KPZ equation. Now, I should be clear, we don't identify all of them. We actually, what we do is we identify for every pair U and V, we identify a stationary measure. We actually conjecture, and there's good reason for this, it's kind of generally believed, that there is a unique invariant measure for every pair U and V. So in a sense, what we're doing is identifying what should be the unique invariant measure, but we haven't proved that uniqueness, let me just say. So what is the statement of the theorem? So first is that for each pair U and V, we show that there exists a stationary measure. And we call it HUV dot. So this is going to be, a function, a measure on functions, spatial functions, which will be statistically invariant, at least its increments will be under the evolution of the KPZ equation with the corresponding boundary conditions UV. Now, just to give you a flavor of what these look like, so for U plus V equals to 0, okay, so U plus V equals 0 really means that the slope on the left and the slope on the right are they're actually the same, right? Because the slope on the right is minus V. So really U is equal to minus V. So U plus V is 0. So in that special case, the invariant measure, sorry, the stationary measure is actually just a Brownian motion with drift U, which is the same as minus V. So this is the case of, remember in my little preface, I said the simplest cases are when you have product invariant measure. Well, this is essentially that, because Brownian motion is just the integral of product measure, the integral of white noise. White noise is the sort of continuum product measure. So this is really like the simple case. When U and V are equal to 0, when you have this alignment of the boundary condition, then you have Brownian motion is the invariant measure. On the other hand, when U and V are not, so for general U and V, the HUV dot, so the invariant measure can be what I'll call stochastically sandwiched between HU minus U and H minus VV, each of which is a Brownian motion, but with a different drift. So what I'm saying here is that you can essentially put yourself between two Brownian motions. So you can put yourself on the same probability space so that the invariant measure for, as you change the boundary parameters, there's some sort of continuity of the nature of the invariant measures. And this is telling you some quantified version of that. Okay, I'm not going to explain right now what stochastic sandwiching means, but I will a little bit later. The final point, which is actually the most important and the hardest point, is that we can actually identify what the stationary measure is, provided that U plus V are bigger than 0. Well, okay, when U plus V equals 0, we also have a description. But this is in physics what's called the fan region. It has to do with the rarefaction fan one sees in something like the Burger's equation. So for the fan region, we completely characterize HUV So the way that we do it in the paper is via its multi-point Laplace transform. So we give formulas for the Laplace transform, which is in terms of something that is called a continuous dual Hahn process. So some stochastic process related to dual Hahn polynomials. I'm not going to go into any detail as to what that is, but there's actually work that is being completed as we speak, and I've seen a copy, so I'll just mention the names. Work of these four compatriots who give a stochastic description, a description in terms of some sort of stochastic process for this invariant measure. And it goes by basically inverting our Laplace transform formula. I should say we posted our paper about a month ago. They didn't solve this in a month and write a paper in a month. We sent them versions of our paper about 2 or 3 years ago. So they've been working on this for a while. It's a hard problem, but it gives, well, what we've done, and then also, using what they've done, it gives a complete description for the invariant measure in half of the parameter space. Just to give you an example of the type of formulas that arise, just to give you some flavor, and this is the only formula I'll write down. If you assume that u and v are bigger than 0, then we get the following formula. So you have a Laplace transform formula. So let me say e to the c, and I'm going to look at, say, the height at 1. So HUV1 is supposed to represent, in the stationary measure, it's supposed to represent this total height difference between the value at 0 and the end point. Okay, so the question is, what is this distribution of this increment? And what we can give is a formula for the Laplace transform, restricted to some set of parameters. So, but still, this is enough to identify its distribution. And it takes a rather compelling form. I wouldn't say so totally simple form, but it takes the form of an integral, simple integral, against a measure, actually an infinite measure, where this measure, mu, this mu c s, can be written as a product of gamma functions. So these are the types of measures that come up when you deal with beta integrals or generalized beta integrals. And these are where the parameters u and v come in these gamma functions. Okay, so I'm just giving you this to give you some flavor of formulas. So you have these gamma measures, these beta integral measures. You take some integral of it and you normalize it by a corresponding term, and this gives you the Laplace transform. And then, as I said, this group of 4 authors is able to actually invert it. And so there's another description that they're going to give of this random variable, and actually of the entire HUV process. Okay, so let's zoom out. So we were interested in the KPZ equation, this stationary KPZ equation. We made some sense as to what it means to solve it. We kind of identified this description, and then you take the logarithm and so on and so forth. And then I told you a little bit, I told you what the long time limit should look like. There's a conjecture, which I'll just state, which is that if you start with any initial data, it will converge to this HUV, assuming the boundary conditions are UV. That's a nice conjecture. Actually, it should converge exponentially fast, and there should be what's called a one force one solution principle, which basically says that if you actually start with your initial data at a time minus t for a large t, and you run it up till time 0, as this minus t goes back to minus infinity, all solutions should kind of coalesce, or at least be kind of exponentially close to each other. Now, what I want to explain in the second part of the talk is, where does any of this come from? Really, how does the KPZ equation arise? And where do how do you get a handle on any of this stuff about the stationary measure? It's not clear it's not at all clear, I would say, where any of this is coming from. Okay, so what I'll focus on for the second half of the talk is a discrete model called the open ASAP. ASAP stands for asymmetric simple exclusion process. And it's a very simple object that's been studied since the late 60s. But it has a very rich structure. And in fact, we'll be dealing with kind of the richest version of it, which is a 6-parameter object. So I'm going to fix a natural number n. And then I'm going to fix 5 other parameters, alpha, beta, gamma, delta, which are positive reals, non-negative reals, let's say. Now I define a Markov process as follows. So I imagine, and you should go back to remember I talked about this idea of a stream and, connecting a lake and a river for those who were there in the beginning. So I'm going to imagine a sort of discrete version of that. So I have reservoirs, which will sit at the left and at the right. And then I have a sort of stream that connects them. Of course, in this stream, water doesn't just go in one direction. It can go both ways. So it's something a little bit more general. I have particles, which are these red dots. Maybe I could put a few of them down. And the rules are as follows. Particles can jump left and they can jump right. And they do so after some exponential waiting times with parameters 1 and q, or q and 1. What I mean by this is, each particle has like a little exponential clock, like some random waiting time that's exponentially distributed, and it has this rate p or q or 1, and it jumps after that, provided it can. Jumps that would result in collisions are excluded. That's the exclusion. And the only other thing I need to tell you about is what's the interaction with the boundary. So the boundary can produce particles or remove particles at both sides. And it does so at these rates alpha, beta, gamma, delta. So in particular, if there's no particle, so if there's an empty site at the left boundary, so this is position 1 through position n, I should say, and the number of sites is n. If at position 1, there's no particle, then you can add a particle after an exponential waiting time with parameter alpha. Or you could, if there was a particle, you could remove it at rate gamma. And on the other side, it's the same, but with beta and delta. So this is a continuous time Markov process. And I'll denote it as tau t. So tau I will represent the location, the occupancy variable. So this will be an element of the state space, which is 0, 1 to the n. So in other words, zeros are holes, ones are particles. And this keeps track of the locations of all of the particles and holes and the evolution of them. Okay. Now there's actually, this might not be so clearly related to a height process, but there's a simple way of relating this to a height process. Let me put another particle in, which is through defining a height function, okay, and looking at the evolution of the height function. So I'll define a height function in the following way. So what I'm going to do is I'm going to draw a sort of piecewise plus or minus 1 slope increment function, which increases by 1 every time it goes into a site that has a particle, and it decreases by 1 when it goes into sites with holes. Of course, I haven't drawn space things out so well, so it's not going to look great. Okay, so now it will decrease, and the last step it will increase. Okay, so hopefully this is clear enough pictorially. Now the jumps that you would try to make correspond to changes in the height function. So for instance, this minimum can turn into a maximum, and it does that at rate q. That corresponds to the particle jumping right, jumping left. And likewise, the maximum here could also decrease into a minimum, and that happens at rate 1. So there's all of these minimums and maximums, and they can kind of keep flipping themselves around according to these rates, 1 and q. At the boundary, you can just kind of flip yourself up or down. And so in this case, you would flip down at rate alpha and up at rate gamma. And on the other side, you do the same sort of flipping, except now you flip down with beta and up with delta. And so you see now you have an alternative description of the process in terms of a height function. I'll call it hn to denote the system size. tx, which x is now a number between 0 and n. Now, because this is a continuous time, markup process, and it has all, nice properties, there exists a unique invariant measure. Which I'll call pi n of tau. So this will be a measure on, all 2 to the n possible configurations, which will be invariant under the evolution of the markup process. So for this tau t process, or equivalently for the increments of the height function. So if I look at this increment process, you see that the increments of the height function are exactly in correspondence with the particle process, right? Because the particles are really derivatives of the height function. So already we're seeing why, for a height function, why the stationary measure will be only for this increment process. Okay. There is actually more information contained in the height function. The height function kind of keeps track of the overall drift of the system, and that's an interesting quantity. But for the question of stationary measure, we're going to focus on the height increments. So what is the relationship between this open ASAP height evolution and this continuous height evolution? Somehow one looks like a discretization of the other, but in what sense? And so what I'll do in the remainder of the talk is I'll first talk to you about the convergence of open ASAP to the KPZ equation. And then I'll talk to you about how do you understand the stationary measure of this open ASAP. And if I combine the two, as the arrows suggest, you get your information about the KPZ equation stationary measure. So this is the sort of picture for the rest of the talk. And so the question we'll first address is, how do you relate this simple discrete model to some complicated stochastic PDE? And this is a subject that's been of interest for many years. There's kind of very important work in the mid-90s of Bertini and Giacomini on, if you look at the full line. In the case of the system with boundary conditions, things are pretty involved, and it was only recently done in work of myself and Hao Shen, and then work that built on that of my graduate student Shaolin Parekh. And the idea is that you apply what's called weak asymmetry scaling, but you also need to take what's what we call triple point scaling. I'm not going to explain the origin of that term triple point, but it will have to do with a certain phase. It has to do with a certain phase diagram for the behavior of this model. This model has very interesting phase diagram with 3 different phases. And this is the triple point between them in which you see the KPZ equation. So just in terms of kind of the parameters that we've defined, let me take epsilon to be something close to 0, in particular n to the minus a half. So I'm going to take n to infinity. Obviously, if I want to get a continuum limit, I need to take n large, and then I need to smush space and time and do some scaling. So I'm going to take n to be n to the minus a half. And now I'm going to take the asymmetry actually to be really close to 1. In particular, I'll take it to be with that same defect. So it's approximately 1 minus 2 times n to the minus a half. So when the asymmetry between left and right jumps is very, very close to 1. The case of a symmetric system is actually much easier to study. You have the symmetry, but you have other properties. You have things called dualities. And so you take a sort of a perturbation away from that of this particular size. Then what you do is you look at your alpha, beta, gamma, delta, and you also take them to be really close to each other. So in particular, you take them to be really close to a half, with a defect again, which is of order epsilon, order n to the minus a half. And you need them to somehow balance each other out. So write it down, but these are where these parameters u and v come in. So I take them to have these defects that are controlled by the parameters u and v. And this almost kind of puts you at a very trivial point. If all of the alphas and betas are equal and q equals 1, the system is super simple and the invariant measure is Bernoulli and the evolution is Gaussian and everything is kind of very nice. But we look at some perturbation around it. And this is the perturbation that creates for us the nonlinearity. And so the result then says that if I take time, I'll use a capital T for a macroscopic time and capital X for macroscopic space, and I look at my height function at scale n, I look at it at a time n squared in a spatial scale of order n. And then I need to scale the whole thing down by this epsilon, by this n to the minus a half. And then there's some centerings, which I'll just write down. I won't go into, because the thing, again, drifts off in one direction. Then this process as a function as a process in t and x, so as a stochastic process, converges as n goes to infinity to the solution of the KPZ equation in these macroscopic variables. So this is KPZ on 0, 1 with UV boundary conditions. And this is provided that, so obviously there needs to be something. So provided that my initial data, so my initial data needs to satisfy some regularity, some Holder regularity, some a priori Holder bounds, and has a limit. Of course, if it doesn't have a limit, you can actually still prove some tightness. You can prove some, subsequential limits solve the equation. But if you want to have a solution to an equation with a particular initial data, you need to converge that initial data. Let me box this because these Holder bounds are actually really important and not at all obvious how you get them for the stationary measure, for which we have very little hands-on feeling for. And so we'll come back to this point a little bit in just a little while. Let me just give you an idea. How in the world do you show that this nice discrete object converges to a nice continuous object? Well, you go through the definition. The definition, and this is a little bit of a trick, and it works well for this ASAP. The definition of KPZ was through this exponential transform, which solved a stochastic heat equation. And so what I'm going to do for KPZ is I actually take a microscopic version, optical, what do they call it? Optical transform. I always reverse them around. Optical transform. And actually, so you look at q to the height function at time t in position x. And miraculously, and here's the the miracle is that this satisfies a microscopic version of the stochastic heat equation. And this is not an immediate fact. This is something that you can verify, but it's obviously going to be a little bit more complicated, but it really satisfies some discrete version of a Laplacian and a rather complicated discrete noise. But it really satisfies exactly the same sort of boundary conditions, just a discretized version, a difference version of these Robin boundary conditions. And so that is the starting point for the asymptotic convergence of this open ASAP to the KPZ equation. Now, but I want to understand something about the stationary measure.
Ivan, can I interrupt for a moment?
Yep.
Could you just give us a drop of intuition about why those are the right scalings in space and time?
Yeah, so good question. So if you look at the KPZ, I'll answer this by looking at the KPZ equation. So if you look at the KPZ equation itself, you can ask, does the KPZ equation have any scalings under which it's invariant? Forget about the boundary conditions for the moment, under which it itself is invariant. And the answer is no, it doesn't. And when you add in the boundary conditions, the answer is no, it really doesn't. Right. But it turns out that if you insert a parameter, let me call it lambda epsilon, and you start to now scale space and time, and you allow yourself to kind of simultaneously scale space, time, and h in this same manner. So you do this sort of 2, 1, a half scaling, or this 4, 2, 1 scaling of time, space, and fluctuations. If you do that and you simultaneously put in a parameter that also depends on epsilon, you know, in some manner. I'm forgetting exactly, you know, epsilon to some power.
Mhm.
And you scale the other things by epsilon to the 4, epsilon to the 2, epsilon to the 1. And you also put in some epsilon dependent power here. So you're looking at kind of a sequence of things. Then the KPZ equation will be a fixed point. So it's a sort of a weird thing, right? Where you look at the equation, you ask, how can I scale it to itself? And you say, well, if I scale time, space, and h, and I change parameters, then it will remain the same. Now, what does this relate to the ASAP? Well, if you kind of imagine that ASAP is already a discrete version of this, which you can kind of see if you stare at the evolution equation, then it tells you that you should apply the same renormalization group, the same sort of rescaling plus scaling the boundary parameters and scaling the nonlinearity. And if you think a little while, you see that the nonlinearity is actually the difference between 1 and q. And so the strength of the nonlinearity, the fact that you're doing this epsilon scaling of q, is related to this weak scaling that is required for KPZ to kind of be a fixed point onto itself. All right, so really there's a sort of, you know, picture which is like you have the KPZ equation and you define some sort of cycle that brings it back to itself under this weak scaling. And now you have ASAP, which naturally wouldn't scale to the KPZ equation, but if you can somehow scale it in the same way, it's going to get pulled into that orbit. Okay. And that's the best intuition I can give.
All right, cool. Thank you.
Going into some calculations. Okay. So the question that we're kind of left with is, how do you start to get your hands on the stationary measure, and you know, obviously you want then to show that it has a limit under this special scaling. And so, you know, I don't have a ton of time, but what I'll try to still give you some flavor for that. And I actually want to start with a description of what the stationary measure looks like in a much simpler setting, which is either the periodic or the closed ASAP. And then I can tell you just a little bit about what it looks like for this much more complicated model. So the periodic ASAP is the following. So you put ASAP, but you don't have boundary conditions. You just have this sort of toroidal boundary condition. So maybe you have a few particles, and they do the exact same thing as usual. They jump left and right, you know, P, or, you know, Q and 1, and they exclude each other. And so you can ask, what's the invariant measure for this system? And the answer is, well, if you fix the number of particles, then it's uniform. You let's look at uniform configuration of k particles over all possible locations. You know, if there's n locations, and you have a subset of them, you just take uniform. So uniform is invariant. Or you could actually take product Bernoulli. So if you just flip a coin and identify particles with heads, then that will also be an invariant measure. So this is a very simple setting. This is like the simplest sort of situation that I alluded to earlier. Now the closed ASAP is also easy to identify the invariant measure. So in this case, alpha, beta, gamma, delta are 0, and you only have particles inside the system, and they stay inside the system. So maybe if you start out with like 3 particles in the system, you'll always have 3 particles for all time later. Now, what you can do in this situation is you can actually identify the invariant measure in terms of the height function. So you look at the height function. So say I go down, and then I go up, and then down, and up, and then down. So this is this is my sort of bad version of drawing the height function. And you see that this height function actually defines a partition, lambda, right? Some rotated version of a partition. And you can show that the invariant measure takes the form q to the size of lambda times the indicator function that lambda lives in a sort of, you know, in a box that it needs to. So if you fix that there are 3 particles out of 6 locations, the box will be a 3x3 box. And so this is actually already, you know, some indication of the interest of these types of measures from the beginning of the talk. This is the measure. This was the invariant measure for the closed ASAP when alpha, beta, gamma, delta are 0. Obviously, when you invoke the alpha, beta, gamma, delta, things will get a little bit more complicated. And so in the last few minutes, I want to tell you a little bit about the nature of these more general ones. And since I'm running low on time, I'll actually hop to a pre-populated version of the talk where I can just save myself a few seconds in writing. So the first thing I want to say, there are two things I'll tell you, and I'll be brief on each one. You can identify the stationary measure using a probabilistic tool and an algebraic tool. The probabilistic tool is something called coupling, and the algebraic tool is something called matrix product ansatz. So the coupling one is very nice, so let me spend a moment on it. So imagine that you have two systems, red and blue, or unprimed and primed. And in the red system versus the blue system, so in the blue system you have the rate at which particles enter the system, the alphas and the deltas, are bigger than in the red system. So the blue system has a faster rate of putting stuff in, but it has a lower rate of removing stuff. So you would imagine, intuitionally, that the blue system will have more particles, right? Is a faster rate of putting stuff in, slower rate of taking stuff out. So it should have more particles. What you can show actually is a sort of, well, it's like this stochastic sandwiching I was alluding to earlier. You can show that the invariant measure of the red system will always be less than or equal to that of the blue system in the following sense. So you can put the two invariant measures on the same probability space in such a way that there will always be more blue particles per site than red particles. What that really means is anywhere there's a red particle, there'll also be a blue particle, plus there'll be other places with blue particles. So the invariant measure kind of can be ordered in this stochastic sense, strictly ordered site by site. So, under one measure, the probability there's a particle at the position 7 will be strictly larger than that of the other system, and same for any other event. How do you actually show such a coupling is a very nice piece of classical probability, and it has to do with what are called second-class particles. So let me take a moment and tell you, and then I'll kind of, the rest I'll be brief on. So what you do is you actually, you color particles. So you imagine you have red particles and then you have blue particles. And the blue particles are everywhere the red particles are, plus there are additional particles in other locations. So if you imagine this sort of initial condition, what you want to do is you want to show that you can simultaneously evolve both the red system and the red union blue system, so that marginally the projection onto just the colorblind system, or there's the red system, will be the correct evolution for the given boundary conditions. And you can do this by constructing a type of particle called a second-class particle, which is basically these blue particles, the particles that are only blue, that are not kind of blue and red. And okay, what I've drawn here, and maybe I don't have actually time to go into it, is the rates that one uses in defining the second-class particles. So anyway, so what this does for you is it gives you a stochastic ordering of the invariant measures. Now, in order for this to be useful, we still need to know how to say something about invariant measures. And really, the main tool that people have used in this direction is something that was introduced in the early 90s, which is called the matrix product ansatz. And it's a really interesting but very hard to work with tool. So it was introduced by Derrida, Evans, Hakim, and Pasquier. And the real challenge is, how do you compute the invariant measure? Obviously, you have a finite state markup process. You can just diagonalize a matrix. But how do you do it in a way that's kind of systematic and for which you can hopefully take asymptotics? And what they showed was that you can do it by actually looking at a quadratic algebra in these two parameters, D and E. So you find operators, matrices, maybe infinite dimensional matrices, that satisfy this quadratic algebra, this sort of this almost commutation relation algebra, with these eigenrelations with some vectors v and w at the boundaries. And if you can find such a, if such a thing exists, or well, you can just define it, you use it to construct, to compute numbers, and these numbers will give you the invariant measure. So you take, here I've written it actually in terms of a generating function for the invariant measure, but you can explicitly compute these sort of matrices called a matrix product. It's like product of these matrices. And you can use this to compute. It turns out that there are very special values of alpha, beta, gamma, delta, kind of a sub manifold of values, for which you actually have Bernoulli product measure, and this gives you that. So in those special cases, these are the special cases that in the sort of limiting picture corresponded to the Brownian motion. So these are kind of a one parameter subset. But in general, it's much more complicated. You don't have this. Really what happens in these special cases is that you can find, this corresponds to being able to find one-dimensional representations for this algebra. In other words, these D, E, W, and V can just be taken to be numbers, scalar numbers. And that's why it's very simple. But for general cases of parameters, this will need to be, any representation will be infinite dimensional. And that's why this is one of the reasons this is hard to work with. Depending on the representations you can find, you can do stuff. So Uchiyama, Sasimoto, Adati found a nice representation in terms of Askey-Wilson Jacobi matrices. So this maybe isn't so surprising if you think about that Askey-Wilson depends on 4 parameters in Q. Maybe the two are somehow going to be related, and they found very nice representation here. There's another representation that is not quite what we use, but in terms of tableau combinatorics, things like Q to the volume, but much more complicated, that Cortile and Williams found. And then most recently, Brick and Wisłowski found a representation for this invariant measure in terms of something that they called Askey-Wilson processes. And I'd love to tell you more about it, but obviously time is running out. But let me just come to the kicker. So the kicker is that these Askey-Wilson processes, so here's like a formula that you get for the generating function of the total number of particles in the system, okay? The generating function gets written in terms of some ratio of integrals which involve some measure, and this measure is related to the orthogonality measure of the Askey-Wilson polynomials. Now, if you've ever seen these Askey-Wilson polynomials, the orthogonality measure is written as a product of a bunch of Q-Ponchhammer symbols, infinite Q-Ponchhammer symbols. And so the game goes that if you want to go from this type of formula to this type of formula, or really if you want to go from these types of formulas to the type of formulas that we get that characterize the limit, you need to take asymptotics of Q-Ponchhammer symbols. And you really need to use these asymptotics. And the reason why the uniformity in epsilon and z is so important is because if you look up here, we're really taking integrals against measures. And these are infinite integrals. And so you need dominated convergence. It really comes back to kind of fundamentals of integration. You need dominated convergence to take a limit. So a lot of the work goes into establishing these asymptotics and then using them to take asymptotics of these Brick and Wisłowski formulas, and then using that as well as the couplings. So the couplings are very important for establishing the Holder bounds that I alluded to. So combining this whole thing gives you the full picture, which is that the open ASEP and its stationary measure converges to the KPZ equation and its stationary measure, and it gives you this this long sought after stationary measure of the KPZ equation, which should be universal and should be in the sense that all initial data should converge to it. Okay, so I've gone over by a minute or two. Hopefully I gave you some flavor for how you can combine probabilistic tools, analytic tools, also some asymptotic tools to extract this sort of information. And I'd be happy to take any questions. Thank you.
First, thank you.